The Rescale platform positions engineering-driven companies to digitally transform new product development. The benefits of a cloud-based control plane like Rescale starts with cloud-scale computing for engineering and flexible and extensible R&D computing stacks. But it doesn't stop there. A unified control plane also serves as a foundation for simulation data management to capture the intent of every simulation and help define a source of truth for simulation data. Rescale can do this by adding metadata to simulation outputs and interface with your systems for data management or model-based systems engineering. Additionally, the unified control plane can also automate sequences of multiple simulations to support engineering processes. Let's see how this can work. Product lifecycle management systems are the systems of record for the products companies design and build. As engineers explore new ways to improve the product, many teams focused on different physics using different tools may perform different studies on various product components. One challenge many organizations face is getting visibility on these activities to better understand how projects are performing and also to minimize duplications of effort. By capturing the intention of each and every simulation with metadata tags, engineering leaders can quickly identify which activities are supporting a particular study and get a sense of progress, costs, and the involvement of individual engineers on projects. But it doesn't stop there. Metadata can not only apply to simulation jobs, but also to other resources like files. Rescale can help identify how files are being used. In some cases, files that were used to run simulations may be later identified to be invalid. This means that any work performed using these invalid files need to be rerun. Because Rescale keeps track of all job runs, including what data was used, resource tags allow us to quickly identify the work that needs to be redone. Defining the sources of truth for simulation data in the data fabric also helps support model-based systems engineering approaches to product development. Evaluating multiple performance measures concurrently is a key part of model-based systems engineering approaches to product design. With each simulation output appropriately tagged for the components and design variants they represent, engineers can more quickly form a full picture of how different design decisions are impacting overall product performance. Finally, many engineered products require multiple computing jobs. Examples include running designs of experiments or using the output of one simulation for the input of subsequent simulations. Computational pipelines will change engineering just as data pipelines have changed business intelligence. In a digital twin example, sensor data from product and operations can trigger simulations that can help identify likely scenarios that may occur. In this scenario, IoT data from an oil platform is passed into the Rescale data fabric, which triggers a series of simulations whose results can be reviewed by teams to identify whether a response is needed to perform preventative maintenance. Computational pipelines also have a role to play in AI-assisted engineering. Many organizations that run physics-based simulations at scale are evaluating ways to use AI to dramatically lower cost, get faster time to answer, and develop intellectual property on how their product designs can perform in a variety of situations. Developing such an ML model requires running simulations across a broad range of parameters to generate the necessary data. Then physics-informed neural network frameworks can be used to train an inference model. Engineers can then use this inference model to identify preliminary hypotheses for new products that best meet specific design objectives. By automating this entire process in a computational pipeline on Rescale, organizations can make this process more repeatable and incorporate insights from additional simulations to further enhance their ML models.